Whether you're talking about dog stars or dog stars, diamonds, or diamondbacks, all normal matter is made from electrons and two other tiny little guys called quarks. Put those three things together, let them interact, and you get all the incredible complexity that makes the universe such an interesting place. But how does that happen? How do you get somebody like Leonardo da Vinci from mixing just 3 different particles? How do you go from such simplicity to such incredible complexity? Let me take you on a journey, and together we just might figure it out. Along the way, we will probe life, consciousness, and the inner workings of the human brain, and just maybe uncover a few surprises. We begin our journey in the world of the small. Basic particles are really tiny. For a long time, people thought these particles had no size at all. But then along came quantum mechanics, which proves it is impossible for anything real to have a size of 0. Today we know that fundamental particles have a real size, called a Planck length, named after Hall of Fame physicist Max Planck. Now a Planck length is so small it's hard to imagine, much less to describe, but that won't keep us from trying. If a Planck length were as large as a grain of sand, then a proton would be the size of the Earth. And an atom would be the size of the orbit of Jupiter. That single grain of sand would be almost as large as the whole Milky Way galaxy. Look at these grains of salt. To the naked eye, they all look the same. But under a microscope, you can easily spot the differences. But every electron in the universe is absolutely identical to every other electron. If we could magically swap every electron in your body with some other electron, there would be no change. You would still be you. When you try to picture the behavior of things this small, you might resort to some really weird science.
Quantum mechanics.
Some really smart folks thought this stuff up, and they made it clear that these fundamental particles don't always behave as you might think they would. Describing an electron is like describing dice at a crap table. There's a 50% chance that the electron will end up here, and a 50% chance that it's there. In 1927, Werner Heisenberg had some new ideas about uncertainty. He said,
For an electron, the more precisely the position is determined, the less precisely the momentum is known, and vice versa.
Einstein thought he was nuts, but the more scientists played with that notion, the more they concluded that subatomic particles can disappear and reappear in another place, and they can do this without existing in the intervening space. When an electron is trapped inside an atom, the places that this activity is limited to is the space around the nucleus, and this makes it look like a shell. Basic particles can also be in more than one place at a time, if the time is brief enough. an electron can travel from here to there along all possible paths simultaneously. And even more astounding, these particles can appear out of the nothingness of space, exist for an extremely brief instant, and then disappear. Scientists call them virtual particles. They may be virtual, but they can have very real effects. It's all this jumping around that makes particle descriptions so inexact. But then existence itself is inexact at these tiny scales. You know, time doesn't exactly behave itself on tiny scales either. Wouldn't you love to be able to travel in time? Authors through the ages have explored this tantalizing idea of being able to travel into the past or the future. Believe it or not, we are time traveling right now, into the future, one instant after another. But the question is, does time only travel in one direction, at one rate? Meet Alabama Slim. He's not only a great pool player, but he's a time outlaw. He's the only one you will ever see perform this particular pool shot. If we watch Slim breaking the rack in a game of 8-ball, we can easily tell if time is running forward or backward. The backward sequence doesn't break any laws of physics, but the coming together of all the right factors to make it happen is so improbable that we can use the words "never happen" and be absolutely right. In striking contrast, when two protons scatter off each other, time seems totally reversible. The backwards version looks just like the forward version. So why is this so different from playing pool? The answer is that the interaction between the protons is simple. Let's take a close look on how we experience time. Have you ever thought about the differences between future and past? The difference between free will and memory? And the difference between hope and remorse? You can narrow and focus your attention so that you observe that split second of what we call the present. The present is now. Now. Well, you get the point. What you're focusing on is the future flying into the past. And if you can remember it, it is no longer in the present. The present, where everything happens, seems to have no extent at all. Something that happens 1 second ago is already the past, and this is true for a millionth or a millionth of a second. Likewise, the future is as close to now as is the past. Okay, while the present is an instantaneous moment for complex objects like you and me, it can be a very different story for electrons and quarks. These particles are described by an equation called a wave function. And when two particles interact, their wave functions become entangled. But for how long? When do they re-establish their individuality? A physicist would ask, when does this wave function collapse? Here's an electron named Henry bumping into one of his brothers. We know that after the interaction, Henry will be in one of two places: behind door A or behind door B. It's possible that for an extended period of time, our time, seconds, even minutes, our electron can effectively be in both places at once. Now you know why Einstein thought these guys were nuts. One way to think of this is that the electron has a flow of time that depends only on the next interaction. Present, for the simple electron, is an indefinite extension. It remains in the present until some new interaction causes it to change its wave function. And once that happens, time has moved forward. Any new interaction can cause the electron to jump from place A or place B, a light shining on it, or an electric field turning on. It does not take an observation or a measurement by a person, an enduring misconception. The collapse of a quantum wave function is the point where the universe moves forward, where present becomes past, and where more than one possibility becomes just one actuality. And time itself becomes irreversible when the collapse effect spreads to enough atoms and molecules that the backward sequence becomes so improbable as to never happen. So we've discovered a possible key in our understanding of complexity. The more complexity, the more improbable it is for time to be reversible. Now let's jump from the small to the large. Here's a musician playing a ragtime piece on a guitar. At this scale, quantum mechanics is totally unnecessary to describe the scene. His atoms and the atoms in the guitar may be dancing around on a scale equal to their size, but none of that has a noticeable effect on the musician or the music. The musician has a reliable and continuous existence. There's nothing reversible in this scene, and there is uniqueness. Unlike electrons that are interchangeable, musicians are not. The probability of finding another musician exactly like this one somewhere else in the universe is virtually zero. Also notice the chance of this musician being able to travel backward in time is equally zero. Since his atoms are dancing about, continuously interacting, causing multitudes of wave functions to collapse, irreversibly changing the possibilities into realities. There is no going back. It is precisely this irreversible and complex process that makes this musician so unique. Back to the small, where we begin our climb up the ladder of structure. There are two kinds of quarks that are found in normal matter. Physicists call them flavors of quarks. These quarks are the up quark and the down quark. A proton is formed from two up quarks and one down quark, while its slightly heavier cousin, the neutron, is formed from two down quarks and one up quark. The red, green, and blue colors of the quarks represent a property that attracts them to one another. It is this color charge property of the quarks that hold them together in a proton or a neutron. These protons and neutrons can then combine to form the nucleus of each element in the periodic table. One proton in the nucleus makes hydrogen. Two form helium. Six, carbon. 8, oxygen. 79 is gold. And 92, uranium. Neutrons help hold the protons together. Because of their electric charge, protons would repel each other more strongly if neutrons were not present, and the heavier elements would come apart. There are approximately as many neutrons in each element as there are protons. Atoms are formed when the positively charged protons in the nucleus capture the negative electrons. Neutral atoms capture one negative electron for each positive proton in the nucleus. So, hydrogen has one electron to go with its one proton. Helium, 2 electrons. Carbon has 6. Oxygen, 8. Gold has 79. And uranium, 92. There are nearly 90 stable elements. The largest of them contain close to 800 fundamental particles joined in a complex but stable structure. But electrons cannot just gather around in a crowd. Once again, the strange, wonderful world of the tiny has its idiosyncrasies. Electrons arrange themselves in shells inside an atom like the layers of an onion. And only 2 electrons can fit per layer. So the more electrons an atom has, the further away from the nucleus the outer shells must be. And that means these electrons are more loosely held. It is this difference in how tightly electrons are held in each different kind of atom that determines the chemical properties of the element. This accounts for the ability of metals to conduct electricity, the aloofness of noble gases, and the formation of molecules. It turns out that protons in 2 or more different nuclei can sometimes capture and fight over the same electron. And when that happens, atoms of different elements are joined together to form molecules. This oxygen molecule is sharing 2 of its electrons with 2 hydrogen atoms. This is how a water molecule is formed. Some molecules can be quite large and complicated. Carbon, hydrogen, and oxygen join together to form some of the most important large molecules. Amino acids are molecules that are necessary for carbon-based life. And recently, it was discovered that amino acids form naturally and spontaneously in the vast gas clouds of outer space. Since these molecules are the predecessors of life, it is important to know how abundant and universal they have turned out to be. Somewhere about here, our measurement of simplicity starts to edge towards the complex. At the level of complex molecules, existence is pretty reliable. Molecules such as adenine are too large and heavy for the uncertainty principle to enter into their description, and quantum mechanical oddities are rarely encountered at this level. but every adenine molecule is still identical with and interchangeable with one another. There isn't sufficient complexity to generate uniqueness. And a movie of even a complex molecule forming looks equally plausible running both forward and backwards. So reversibility still indicates simplicity. Stars, like our own sun, form from gas clouds that have about every kind of element there is, as well as some pretty complicated molecules. Stuff left over after the sun forms usually turns into a system of planets. Some of these planets have a solid surface, perhaps liquid seas, and a gaseous atmosphere. A rich environment for atoms and molecules to come together in a complex chemical reaction. Carbon atoms in particular link together to form complex organic molecules and amino acids. Chemical catalysts speed reactions along. The products of one chemical reaction become the raw material for new reactions. At some level of complexity, a catalyst becomes an enzyme. An amino acid chain becomes a protein. A loop of chemical reactions become a metabolism. And chemistry becomes biology. On our planet, and perhaps countless others, life arose. The DNA molecule, which is the basis of all organic life on Earth, is more intricate by far than any spiral galaxy. Because the structure of DNA contains something new, something that was missing from inanimate matter before the origin of life. It contains information. The DNA molecule encodes not only the information necessary to make copies of itself, but the information necessary to construct an entire organism. The blueprints for an ant, or a dolphin, or a bullfrog, or even a person. All of this information is somehow built into the structure of an organism's DNA in a molecular code billions of letters long. This information wasn't always there. The first DNA molecules could probably do nothing more than make copies of themselves from the surrounding molecules. This self-reproduction is a fundamental aspect of what we call life. And once there was life, a new set of rules took over. The laws of natural selection. Life became matter that evolved as a result of environmental pressures. Matter that changed randomly. But those changes only endured if they improved a life form's chances of survival in each environment. Change with a purpose. While a species' evolution is determined by the interaction of random changes and environmental pressures, changes in an individual life form can be the result of an organism's reacting and adapting within its own sphere of influence. It can push back at its environment. The better a system was at making copies of itself, the more copies there were in the next generation. As the first living organisms adapted to ever-changing environments, a greater diversity of living things arose. A side effect of this increase of diversity was increased complexity. Now, all of our tests point ever more towards the complex end of our complexity meter. Consider a living single-celled organism. There's nothing reversible about life or death, or eating or being eaten. And there is uniqueness. Unlike electrons that are interchangeable, even single cells are absolutely unique. They may be capable of the same functionality, but they are always different in form and structure. Single cells soon join together to form multicellular colonies. And cells in these new colonies, once functionally interchangeable, became increasingly specialized. Some cells did the digesting, others became responsible for movement. Specialized cells led to the specialized tissues and organs. And most importantly, cells that could respond to light, or electricity, or chemical disturbances evolved into full-fledged nervous systems. For centuries, the standard approach of science has been to understand nature by breaking it down into smaller and smaller pieces. Consider a flower. If we were to study flowers in their natural environment, their various forms and features, that makes us botanists. But in order to really understand how the flower works, how photosynthesis keeps the flower alive and allows it to grow, we have to get inside the flower. We might then study the cells that make up the flower, how the parts of the cell function, and how they are similar to cells of other living organisms. A cell biologist seeks to understand the flowers on this level. But in order to understand how the cells function, we need to understand the complex biochemistry of the cell's metabolism. And in order to understand how the flower's cells divide and reproduce, we have to understand the operations of DNA. The biochemist and the geneticist then seek to understand the flower on a deeper level. The study of organic molecules and DNA takes us down to the level of basic chemistry. How do atoms and molecules interact and combine with one another? This is the realm of the chemist. And understanding the forces at work inside atoms is the job of the physicist. Through this approach, breaking down the flower into smaller and smaller parts, and understanding how those parts function, we have built up a deep and comprehensive view of the laws of nature, from biology down to chemistry, and from chemistry down to physics. But there's a limitation with this approach. Somewhere along the way, we lost the flower. In other words, by breaking the flower down into smaller and simpler pieces, we've lost sight of the complexity that makes the flower what it is. Is there a different approach? Is there some better way to understand complex systems? Not by examining how their parts function, but by understanding how the parts come together to create something that is, in a sense, more than just the sum of its parts. Some scientists believe that order and complexity are inevitable. The study of systems as diverse as board games, computer programs, and ant colonies has revealed some remarkable features of complex systems. Rules much simpler than those of physics and chemistry can result in a great deal of complexity. Consider a board game like chess. The game is based on a simple set of rules. Even young children can learn the rules of chess well enough to play. But while the rules of chess are simple, the game is incredibly complex. It has been estimated that the total number of possible chess games is greater than the number of quarks and electrons in the entire cosmos. With only 32 pieces operating under a simple set of rules, the complexity of the chess universe is astounding. Where does the complexity of the game of chess come from? It's not the individual moves of the pieces, it's the way those pieces affect one another. The way each move depends on the previous turn. The way the possibilities multiply each time a piece is moved. Nature gives us a lot of examples of complex behavior emerging from the interaction of many individuals. The members of an ant colony are capable of a wide variety of complex behaviors. Finding and transporting food. Constructing elaborate underground complexes of tunnels and chambers. Defending their territory from invaders. Such activity would seem to involve a great deal of planning, memory, and coordination. But there's no head ant that draws up the blueprints of a colony and gives directions to the worker ants.
Turn that tunnel to the left. Bring that piece of sand over here.
Instead, each ant follows a very simple set of rules, based on cues from its environment and from activity of ants nearby. For example, how do ants know to walk in a single file to pick up food and then return in a single file to the nest? They don't. They know 3 simple rules. First, if you come upon something that smells like food, pick it up. Second, when you pick up a piece of food, release a chemical signal, a pheromone. Third, if you come across a pheromone trail left by another ant, follow it. Let's see what happens when a group of ants follow these 3 simple rules. The first ant wanders about in its environment and picks up a piece of food. She releases a chemical signal and begins to leave a trail. As the ant continues to wander, other ants stumble upon her trail. They follow this trail and are led to the food. Some of them may follow the trail the wrong way, but that's okay. Once the first ant reaches the nest, she drops off the morsel of food. And when she exits the nest again, she will come upon her own pheromone trail and follow it. The ant doesn't remember where the food is. She doesn't even know that she's following her own trail. She's just following rule number 3. Always follow the trail. Meanwhile, more and more ants have come upon the original trail and followed it to the food. As they follow the first ant's path back, they strengthen and refine the chemical trail. Soon, the ants will appear to march in single file to the food and back. There's no plan, no memory where the food is, no need for a leader to point the way. 3 simple rules, a few environmental clues are all that is needed to orchestrate this remarkable, efficient process. From dog stars to dog and paw stars, we are now embarking on the age of robots. The enormous complexity of living things has been brought sharply into focus by our efforts to create machines that mimic organic living creatures. We now have robots that help in many fields: bomb disposal, fire and rescue operations, hospital care, military drones and tanks. Our desire to build robots seems boundless. Indeed, robot building competitions are held annually at many high schools and colleges across the country. We now have robots that can fly planes. Can you guess which plane is being piloted by a robot? On the other hand, the robots that explore other planets can certainly perform feats that no human should attempt. From laser eye surgery to automobile construction, we have been quite successful in building robots that can perform remarkably well in situations that can be defined by simple rules and repetitious tasks. Similar to the way ants can perform tasks following simple rules, pool robots clean by moving around in random patterns that eventually cover the entire pool bottom. The tail sweeps back and forth to raise bottom debris while the water vacuum sucks the dirt into the container bag or net. And occasionally it backs up to avoid getting caught in corners. Vacuum cleaner robots perform their duties by very similar algorithms. The efforts to equip robots with cameras for eyes and other parts to mimic living creatures have met with considerably less success. Only very recently has there been real progress in creating androids, robots shaped like humans that can exhibit a wide range of our muscular and motor functionality. But we are still at the starting line when it comes to creating machines that can mimic human thought. It is easy to imagine an ant or a robot as a mindless agent following simple rules that produce the illusion of complexity. But what of a human mind? Surely everything that humans do, from designing skyscrapers to composing symphonies, is not the product of a few simple behaviors. And yet it might be. Because everything that humans do, or think, or feel, is a result of these basic units of brain structure, the neurons. The human brain contains more than 100 billion neurons. Just like a single ant could never build an anthill, a single neuron can't think or feel or remember. A neuron's power is a result of its connections to other neurons. Each neuron is connected to as many as 1,000 of its neighbors. These trillions of connections provide the playing field upon which the complex activity of the brain takes place. Each neuron can turn its neighbors on or off depending on the signal it sends. And the resulting stable patterns of neuron firing represents memories and images and thoughts. We don't yet understand the relationship between neural activity and mental experience. We don't know what the precise pattern of memory or an image or a thought looks like. We don't yet know how to read the cerebral code of the neurons. But by looking at the behavior of other complex systems from anthills to computer simulations, we may yet learn some techniques that allow us to work our way up from the activities of a few neurons to see the structure that emerges from the whole. It is possible to view the entire history of the universe as a story of complexity emerging again and again from simple systems under the influence of simple rules. The laws of physics bind together the most fundamental constituents of matter, electrons and quarks, into stable structures called atoms. Atoms themselves are subject to new sets of rules, pushing and pulling together and combining into new forms, molecules, governed by the laws of chemistry. Simple molecules of water and carbon dioxide, consisting of only a few atoms, can combine and interact in even more complicated ways, building more and more complicated structures, clumps of chains and rings. The rules of chemistry are universal. The same kind of amino acids that are found in our own bodies can also be found in the cold depths of space. At some point, very large and complex molecules become capable of something new. DNA molecules make copies of themselves. The chemical metabolism inside of a cell produces and stores energy. Energy that can be used for motion and reproduction. The raw material of chemistry has given rise to new kinds of complex behavior, one that we call life. Large multicellular organisms involve a whole new class of structures. Cells provide tissues and organs and organisms of greater and greater complexity. Driven by natural selection, yet another set of laws. Life has been able to diversify and take more and more complex forms. From the first organism that can sense the environment and react to light, neurons led to nerves, and nerves led to brains. At this level of complexity, an organism can gather information with its senses and then use this information to influence the future. What a concept! The human brain is perhaps the most complex structure in the universe. And in its complexity comes the most mysterious phenomenon that science has attempted to understand: consciousness. At this level of complexity, not only does the organism gather information and use it to influence the future, but it can take notice of itself doing this. It can influence the future with intentions to change itself. It can also cause changes to its species through direct modification of its own blueprint. Genetic manipulation, a directed evolution. Wow. So from three fundamental particles, we have now constructed an organism that is alive, conscious, self-aware, and has the ability to understand itself and the universe it occupies. How wonderfully complex.
Checking out traffic this morning along the Keighley Gardner, Guy Valentine.
It's a bit of a battle for drivers without cover. I'm talking if you don't have any shade, you're fighting some pretty bright sunshine.
And also caution on Highway 7 going east of Mayfield.
And northbound Don Valley Parkway on the ramp to eastbound 401, we've got a disabled vehicle.
June the 14th, 2002. It was just another busy workday with all the usual hustle and congestion. With all the close calls and near misses that people all over the world have come to accept as the normal level of risk in everyday life. But on that day, high overhead and behind the sun, what no one saw coming, what no telescope on Earth was able to see against the blinding light, was an asteroid big enough to destroy an entire city. From behind the sun, asteroid 2002 MN came hurtling towards Earth, faster than a speeding bullet. It shot past, less than a third the distance to the moon, and nobody saw it, until 3 days later, when the rock emerged from Earth's shadow into the night sky, going away.
It looks like the Earth just dodged a bullet. Actually, it was an asteroid. Scientists say it blew by last week at a distance they describe as a close shave.
The airline industry would call this a near miss. Scientists who study asteroids and comets called it a problem.
The threat of asteroid impacts on the Earth is very real. We know that throughout history this has happened. The craters we see on the moon are examples of the kind of impact history that the Earth has had. But it also happens very rarely. So it's a very unusual kind of hazard. It's a hazard in which the risk in any one year is very low, but it does happen, and if it really did come about on our watch, it could end civilization.
These cosmic bullets originate on the far side of Mars, in the main asteroid belt, where a bracelet of celestial debris circles the Sun. Millions of rocky fragments, building blocks of a planet that never quite came together when the solar system was formed. What's often depicted as a busy cosmic junkyard is actually more like a big empty speedway. The rocks are far apart and moving very fast, ranging in size from pebbles to boulders to rocks the size of Mount Everest. Occasionally, the tug of Jupiter's enormous gravity drags an asteroid off course, causing it to crash into another asteroid. Some veer away into new orbits that cross the paths of Mars, Earth, Venus or Mercury. Another ring of debris called the Oort cloud is the source of most comets, which are big, rocky ice balls that orbit the Sun and cross the paths of the inner planets. All the inner planets and our Moon bear the scars of numerous asteroid and comet impacts.
We do get hit all the time by pieces of debris from asteroids and comets. In fact, 40,000 tons of cosmic debris plummets into the atmosphere every year. We see them every night as shooting stars. They don't hit the Earth very often, but when they do, clearly it isn't just going to be a matter of a shooting star seen in the sky. So it is inevitable. It's only a matter of time before the next big one hits us.
Even small rocks can make a big impression. In 1908, about 2,000 square kilometers of Siberian forest were instantly flattened as an asteroid exploded near the Tunguska River. The impact site was so remote, researchers had to mount a wilderness expedition just to find the place. When they arrived, there was no crater. Paintings, based on eyewitness accounts, described a fireball. A horrendous explosion in the sky.
Didn't actually come crashing down to the ground. It exploded maybe 5 to 10 kilometers up in the atmosphere, and that made a big blast wave in the atmosphere, and that is what did the damage.
All this was caused by a relatively small asteroid, somewhere between 50 and 100 meters across. Roughly the same size as asteroid 2002 MN, the one we couldn't see coming. Tunguska's 2,000 square kilometer blast wave would have leveled London. But as bleak as the thought of cosmic collision may be, there is at least a glimmer of hope.
One of the special things about the asteroid impact problem is that unlike the weather or earthquakes or other natural hazards, we, at least in principle, we could do something about it.
And when we know one's coming for us, our claim is that the technology is available today to stop it.
On the Earth, we've got active geology, we've got volcanoes, we've got earthquakes, we've got continental drift, we've got rain, we've got wind, we've got storms, we've got snow. All of those things erode away craters, and that, in some ways, actually fools us into thinking that indeed the Earth doesn't get hit as often as it actually does.
Counting craters on the Moon and then estimating how often the Earth gets hit can be a pretty sobering exercise. One scientist who made that kind of calculation was astronomer Ernst Öpik, who published his impact estimate back in 1951. The general public, however, paid little attention to the science or the implications. But one individual who did take the issue to heart was Lembit Öpik, the astronomer's grandson, who got himself elected to Parliament.
My grandfather is the reason why I carried on in politics, what he initiated in science. In essence, he was a pioneer. He saw the danger of asteroid and cometary impacts with the Earth, and he had the courage to speak up about them. And he did that at a time when it wasn't really taken seriously, in the 1950s and 1960s.
After years of pushing and prodding, Lembit Öpik convinced the British government to commission a comprehensive scientific study of the asteroid and comet threat. The expert conclusion was, the threat is indeed real.
Now, the government has set up a task force to examine the risk of an asteroid hitting the Earth.
Still, skeptical politicians might want to get on the bus and take a trip to the Natural History Museum. Ask any schoolchild who's been there recently, and you'll hear a fascinating and truly scary tale about what happened to the dinosaurs.
The dinosaurs were alive here. They were dead when this sediment was deposited, and this layer is one of the most unique layers in Earth history.
In 1980, the discovery of iridium beside a layer of clay which marked the end of the age of dinosaurs led Lewis and Walter Alvarez to publish a theory that a huge asteroid or comet had hit the Earth 65 million years ago and wiped out the dinosaurs. But for this concept to be confirmed, there had to be a crater. There may be tons of dinosaur bones in these dry canyons, but where on earth was the big crater? Just the kind of mystery a budding young scientist would love to solve.
When I went back to...
Off the coast of Mexico's Yucatan Peninsula, Dr. Alan Hildebrand investigated a huge gravity anomaly discovered by oil drillers back in the 1950s. Put that together with a semicircular magnetic anomaly and you get a massive crater, 180 kilometers across, near a little village called Chicxulub Pueblo. Most of the crater is underwater now. Erosion and continental drift have covered the visible evidence. But 65 million years ago, this was ground zero.
This object would have fallen through the atmosphere in just a few seconds. It's going through the sky, it would have been brighter than the sun. As soon as it contacts the surface of the shallow sea in Chicxulub, of course, it starts propagating the shock wave down into the planet, and it keeps pushing into the planet, and it only gets stopped maybe about 30 kilometers down. The pressure wave would have traveled around the entire planet in the atmosphere. You could have heard the impact on the other side of the planet. The giant impact fireball rising out of the hole, it would have risen, say, 10,000 kilometers above the surface of the planet. Near the impact site, it would have been so hot, it would have evaporated the clouds and been hot enough to make the forest, even a green forest, begin to burn.
For Alan Hildebrand, finding that crater pretty much clinched the argument. Planet Earth had been all but sterilized by a rock the size of Mount Everest.
3/4 of the species of large animal life went extinct.
We have made the case. We've got the qualitative information and we've got the statistics to show that there is a very serious risk.
If you wanted to save planet Earth from cosmic disaster, where would you find people with all the right stuff to do the job? Well, Houston, Texas might be a good place to start looking. This town has that rarest of breeds, the space cowboy. Houston is home to NASA's Johnson Space Center, where rocket science is a way of life and astronauts learn their trade.
If you could roll me 90, then go down. I'll come in on my side.
Behind a swimming pool big enough to swallow an apartment block, you'll find a small research lab, where the rocket engine of the future is being built and bench tested.
Yeah. Mm-hmm. Very nice. Question is, how big is the plasma going to go from here to here?
Dr. Franklin Chang Diaz is one of the lead researchers, as well as an astronaut with 7 shuttle missions under his belt.
And in fact, there was a time in one of my flights where we got hit by very tiny micro meteorites, perhaps, or some sort of orbital debris, which made little tiny dents or little craters in the windows of the shuttle.
Well, that tube is welded. Yeah, I did it. We already welded it. Yeah, I did it.
First-hand experience with rocks in space gave birth to a new idea and a dual purpose to Chang Diaz's work here. His rocket engine has been developed for long-distance missions to Mars, or as far away as the icy moons of Jupiter. But it could also be used to push a dangerous asteroid out of harm's way.
I am concerned enough to think that we need to not waste time arguing about it as to whether it's real or not. I think we need to move ahead and do them.
Well, I'm wild and the hell's free. Come on, baby, you belong to me. Sweet kiss makes my engine start. Well, I'm wild and the hell's free. Come on, baby, you belong to me. Sweet kiss makes my engine start. The way you move, you own my heart. Sweet kiss makes my engine start. The way you move, you own my heart.
If this is a threat which has a very low probability, all it takes is one, and we are history.
But before we can send a spacecraft chasing after a rogue asteroid, we have to know where to look for it. In the American West, if you drive across the desert to the White Sands Missile Range in southern New Mexico, you'll find the most powerful and effective asteroid hunter on Earth. Scientists here have tested everything from rockets to the very first atomic bomb. Today, across the valley floor from the Trinity bomb site, the US Air Force has installed one of the world's most advanced telescopes. This state-of-the-art technology was developed by MIT's Lincoln Laboratory as part of the Star Wars anti-missile defense system. These may not be the world's biggest telescopes, but they clearly are the best when it comes to finding deadly rocks in space. This is LINEAR, the Lincoln Near-Earth Asteroid Research Facility.
On a given night when we scan the sky with this, we'll find perhaps 10 to 12,000 moving objects in the sky. Now, most of those are main belt asteroids and as such don't represent any danger to Earth. But on the other hand, something like half of those will be brand new discoveries, and buried in there will be 1 or 2 near-Earth objects.
Because the Earth rotates, the sky is always moving overhead. To get a clear picture of an asteroid, you have to make the sky stop moving. And you do that with a telescope that can track or follow the stars. This way, you can take time-lapse pictures that isolate the blur of fast-moving asteroids against a crystal-clear sky. It then records these pictures like a TV camera on a computer chip that has 20 times more detail than the picture you're now watching. The LINEAR computer deletes previously known stars and planets, leaving a less cluttered time-lapse sequence of the new discoveries. At the end of each night shift, LINEAR's thousands of new discoveries are emailed to the International Astronomical Union's Minor Planet Center at Harvard University. a team of only 3 scientists must cope with the avalanche of new sightings, searching for potentially hazardous asteroids or comets. Computers make a rough calculation of an asteroid's orbit, but it's up to Brian Marsden to estimate the level of risk.
They may be reporting 50 or 60,000 observations from one night, and it takes a while to get through that. But so we look first at the fast movers and see if there's anything interesting there. H is equal to sine delta. We do sometimes get close to 70 or 80,000 observations a day, almost 1 per second. There are some days when we effectively have 1 observation per second.
Even with fast computers, Marsden's team can make only a preliminary calculation of each asteroid's orbit. 5 shots in one night cover only a tiny segment of an asteroid's orbital path.
You can't solve for the orbit completely from that, but the fact that you're seeing motion over a half an hour or an hour, something like that, does allow us to get a partial solution for the orbit.
Refining the orbit gets complicated. When 2002 MN shot past, its trajectory was warped by Earth gravity, and scientists at NASA's Jet Propulsion Laboratory in Pasadena, California, had to add that to their calculations.
Here's an animation I put together of the asteroid last year, which was discovered after it passed by the Earth.
An elite team of mathematicians and celestial mechanics is now working full-time on a computerized warning system.
Our orbit animation, you can see how when it returns out to the asteroid belt, the close approach to the Earth has changed its orbit, and it's no longer returning to the same place it started.
Because 2002 MN will circle around the Sun and come past us again, the NASA Orbital Mechanics team will have to adjust the calculation in order to know whether it will ever pose a danger to Earth at some point in the future.
So here we've zoomed in on the Earth-Moon system and we're looking down. You can see how close it came to the Earth. It went over the top. And how you can actually even see the bend in the trajectory. So it's a great example of how a close approach to the Earth, or in fact any planet, can be used to, or can significantly change in orbit.
To know where an asteroid is likely to be in the future, you need a model of the solar system. Mechanical models that show the relative motions of the Sun and planets have been around since the early 18th century. They're called orreries. What the celestial mechanics at NASA had to do was create a new digital model. One that includes the gravitational attractions of all the planets and the Sun, and all the other forces that can affect where an asteroid might go.
You just compute what forces are acting on this particular asteroid from all the planets and many of the minor planets in the solar system, and then we can actually trace the motion of that object around the solar system for hundreds of years.
For scientists, the acid test of their mathematics came when a strange new comet raced toward Jupiter. A stream of cosmic bullets that would shock and amaze millions here on Earth. In the spring of 1993, the eyes of the world turned almost in unison towards a doomsday rock like no other. From the far side of the solar system, it flew in a death spiral toward the largest planet. Gene Schumacher, his wife Carolyn, and their colleague David Levy had discovered an odd-looking streak of light that turned out to be a fractured comet. 21 large chunks of icy rock and cosmic dust heading towards Jupiter.
We knew we had something very unusual. It was so unusual we were a little unsure just what we were dealing with.
NASA asked Paul Chodas and his team to calculate the orbit and predict whether this new comet would actually hit Jupiter.
And it started off at some 60%, and before long it was 90%, and this was a year before impacts. As the impacts approached, we continued to predict not just the impact probability, which went very high, but where and when the comet fragments would hit the planet. And it was a prediction months in advance, and as we got closer and closer to the impacts, I kept wondering, well, is the math right? Will this actually happen the way it was predicted?
A giant comet is on a collision course with Jupiter.
Everybody on Earth who was paying any attention wanted to see if the comet would actually hit Jupiter.
We have liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
NASA's Hubble Space Telescope set its sights on the planet, and the pictures of what happened next were truly stunning.
Right there! Oh! Get it! Wait.
And then the impacts occurred. We were within minutes of getting the right answer on the time of impact, and the location of impact turned out to be just right.
Over the next week, 20 more fragments of the comet crashed into Jupiter, some leaving scars as large as the Earth.
Bang on its cosmic schedule, the comet's first impact was recorded by NASA within the last hour.
When fragment G slammed into Jupiter, releasing an amount of energy equivalent to about 6 million megatons of TNT.
In the wake of SL9, a group of concerned scientists gathered in Italy for a brainstorming session. They created a brand new international organization called the Space Guard Foundation.
Okay, I'm going to join.
To promote the discovery and study of near-Earth objects.
Some people imagine that there are lots of astronomers out there scanning the sky looking for incoming comets and asteroids, and that, of course, is not true. In fact, until recently, there was hardly anyone out there looking.
It's going to glow for about a half an hour and set everything on fire around you.
But whose job is it to defend planet Earth? Weapons scientists from the United States and Russia had already held a series of meetings and came up with their own ideas about how to deal with the impact threat.
Blow off some material, you get a reaction in this perpendicular direction.
The military establishment under Star Wars had created a whole lot of devices, or at least concepts, for weapons in space and devices in space. And in the early 90s, when the Star Wars program was looking a little bit iffy, I think there was some motivation for them to try to apply their technology to this newly discovered hazard from asteroids and comets.
The military approach to the problem proved to be controversial. The notion of sending nuclear weapons into space generated an immediate backlash.
Edward Teller was proposing that we blow up an asteroid to show that we could protect the Earth, and I thought that was a pretty crazy idea. Blowing up an asteroid with a big bomb has a lot of problems associated with it, violating treaties, taking a single asteroid and making a swarm of smaller asteroids. It seemed like it was more interest in bombs than it was a serious interest in defending the planet. For NASA, on the other hand, NASA obviously is the natural agency to discover the threat and the objects, but they say no, planetary defense, that's a military obligation and not an obligation of NASA.
Not NASA, not the military. Just when it seemed planetary defense was nobody's job, a tiny speck in the sky would set off doomsday alarms around the world. On a winter's night, the 6th of December 1997, a dim streak of light moving through the constellation Cancer was captured by a telescope in the Arizona desert. Big enough to destroy civilization as we know it, asteroid 1997 XF11 seemed to be heading towards Earth. The initial sighting by the Kitt Peak Observatory in Tucson, Arizona, was relayed to the Minor Planet Center at Harvard University in Cambridge, where a computer made the first rough calculation of the orbit. They were pretty sure it would miss the Earth on this pass, but it would be coming round again, and it looked like there could be a problem in 30 years.
There were indications of close approach to the Earth in 2028. That was about 45,000 kilometers, which really was rather close.
With only a handful of sightings, the orbit calculation remained very rough. It was hard to tell where this rock was going. So Brian Marsden posted a bulletin asking astronomers around the world for more observations before the rock became too faint to see.
I was saying, hey, get your big telescopes onto this. On the one hand, we're only going to be able to observe it for another month or so. We want to improve the orbit calculation and find out exactly how close it is coming.
But one line in the bulletin said that the chance of a collision was small, but it was not entirely out of the question. Within hours of the website posting, reporters discovered XF11, and doomsday headlines screamed around the world. Because the close approach in 2028 would put the asteroid nearest to Europe, London newspapers focused on the exact moment life on Earth might possibly end.
Pictures of it on the internet show it as a tiny moving blob. Scientists have calculated its path in the year 2028.
Watch very carefully. September, October the 28th, the two coalesce.
But at NASA's Jet Propulsion Laboratory in California, the orbital dynamics team thought there must be some mistake.
Asteroid's orbit was affected by it. To my great surprise, when we ran our software, it said that the probability of impact of this particular asteroid in 30 years was essentially zero.
As it turned out, the end-of-the-world asteroid would miss the Earth. That big rock in space posed no threat after all. A frantic hunt through the archives at NASA had turned up photographs of XF11 taken 8 years earlier.
And as soon as those were placed into the orbit determination process, they confirmed the fact that there was no chance that it could hit the Earth in 30 years.
The public at large was not understanding uncertainty in this. They wanted an immediate answer. Is it going to hit us or not?
But people were paying attention. One side effect of the false alarm was that public and political awareness of the threat had been raised. 2 months after XF11, new hearings were held in Washington and NASA was told to speed up the science of asteroid detection. Finally, it seemed, there was a political will to do something. Congress gave NASA a 10-year deadline to search the skies and get a fix on the largest of the doomsday rocks. They called it the Space Guard Survey. While astronomers geared up to search the skies, Hollywood was going into overdrive.
I would go to every dinner party and I would say, are you aware what would happen if a comet was actually on a collision course with the Earth?
Oscar-winning screenwriter Bruce Joel Rubin was hard at work on the remake of a sci-fi classic. The new film, called Deep Impact, would be a Steven Spielberg production.
When we arrived at our hotel in New York, the porter was so incredibly careless with our bags. And the room they gave us, it was beautiful. A broom closet. But the worst part was the shower. My wife drying herself with the
Egyptian cotton towels.
Shower curtain defined that whole vacation for her. Don't just visit New York.
Visit TripAdvisor New York.
With millions of reviews, a visit to TripAdvisor makes any destination better.
An army of scientists work desperately to build this giant rocket, this modern Noah's Ark, to carry a few picked survivors of our doomed civilization.
I think the thing that was hardest for me was the realization that people would have to be chosen to survive.
Let's take the ship away from them! Come on!
Probably a very, very small percentage of human beings would be left on the Earth able to survive something of the intensity of the comet that hit and destroyed the dinosaurs. So I felt making this movie is not just a mission to tell a good story, it's to change minds. It's to let people go, this is something real. This can happen to us. This movie is a wake-up call. It's not just a Hollywood movie, it is pointing at you.
As Hollywood released Deep Impact, telling the world in no uncertain terms that cosmic collisions were no longer just a cosmic joke, real-life professional asteroid hunters were making movies of their own. But instead of using cameras, they worked with delayed Doppler radar. Take the same technology behind a police radar system, jump the power to 400,000 watts, and you've got NASA's Deep Space Network with huge multi-dish systems like the Goldstone tracking station in California's Mojave Desert.
This is the main room of the pedestal of DSS-14.
The first time radar astronomer Stephen Ostro bounced a signal off a rock in space, a wobbling blot of pixelated data bounced back. What looks like digital gibberish spoke volumes to Steve Ostro.
Radar really does three things at once. One, it works at long wavelengths, so you're sensitive to structure on large scales and metal concentration. The other is you can make pictures. And you can't do this from the ground in any other way. You make pictures of objects, and then we take a sequence of pictures, and we go through a computational process to produce the 3D models. That's the second thing. The third thing is that it makes very precise measurements of distance and speed.
When the 1,000-foot radar dish at Arecibo in Puerto Rico bounced a beam off an asteroid called Castalia, the data was translated into a 3D computer model. The very first radar movie showed how Castalia spins and revealed that it was actually two massive chunks of rock held together by weak gravity. Every time they made the trip to Goldstone for a new radar target, Ostro and his team were like kids reaching into a box of chocolates. They never really knew just what they would find. Asteroid Cleopatra, shaped like a dog bone, was roughly the same size as the state of New Jersey and was made almost entirely of metal. Echoes from asteroid Toutatis produced images of a rocky, cratered surface and a wobbling, tumbling spin.
Every single one of these objects that we've made a shape model of is very different. This is Toutatis.
From a telescopic smudge of light to a 3D shape model, radar gave them physical details and the first clear idea of what asteroids are really like. In the year 2000, the radar movie crew developed a dark and mysterious new image, asteroid 1950 DA, a big rock that gave everybody a bit of a shock.
Once we got the radar data, we began the normal process of just seeing how far in the future we could predict this thing before the uncertainties in the orbit blur out. And in this case, we could go over 880 years into the future. And what was startling about that case was the impact probability turned out to be non-zero.
Non-zero means there is a chance this rock could hit us. On March the 16th, in the year 2880, 1950 DA will cross the Earth's orbit. Will it hit us? The odds? 1 in 300. If 1950 DA does hit the Earth, the most likely point of impact would be at sea. Of all the big asteroids discovered thus far, this is the most dangerous one we know. Eric Asfaug and Stephen Ward have created a computer model of the impact.
Yeah, it's kind of funny how this started. It was with the movie Deep Impact, and I was getting phone calls. Lots of people were getting phone calls about the movie, whether it was accurate, the big cresting tsunami coming across.
The concept here is that this asteroid, which is about 1 kilometer across, will hit the ocean at 17,000 miles per hour, and it'll blow a hole in the ocean about 19 kilometers across and all the way to the bottom. And so when this huge hole of water gets blown into the ocean, the water will run back in again, and it overshoots and it collapses and overshoots many, many times, and each time it pumps out a wave. So it starts out hundreds of meters high, comes ashore on the coast of North America at about 50, 60 meters. Up toward Canada, Grand Banks, it's about 40 meters, 20 meters here in the coast of South America, and about 15, 20 meters all the way over to Europe. These waves would run inland about 4 kilometers. So pretty much everything within 4 kilometers from the beach would be covered up repeatedly. And so we'd pretty much be wiped away like you're scrubbing the floor. You know, just scrub like this, and it's pretty much all be carried back out.
In February 2001, a NASA spacecraft called Near Schumacher made the first ever landing on a chunky, pockmarked rock named after the Greek god of love. Asteroid 433 Eros is 33 kilometers long and 13 kilometers wide, one of the largest near-Earth asteroids. The pictures were spectacular. The data will take years to process. Proving that they could land on an asteroid was a major achievement, but in the end, they still don't know much about what's inside. How dense? How tough? How brittle or crumbly is it? What would happen if they gave it a good shove? The surface appearance of any dark and mysterious object can be very deceiving.
So these two spheres, as far as I can tell, have exactly the same mass, the same compressibility, the same color. If I were a spacecraft orbiting these and these were asteroids, I'd be very hard-pressed to tell which was which. Yet, if I dropped them from a height, and only one of them bounces, really illustrates the fact that one of these responds elastically and one of these responds like a lump of clay. And it's critical to really go and find out what's inside before we even start thinking about moving these things around.
When a 3D model of the asteroid Castalia got smacked in a computer simulation, a problem occurred. An impact with the same energy as the Hiroshima bomb turned Castalia into a pile of rubble, but did not deflect its trajectory in any significant way. But there are other ways to apply force to deflecting an incoming asteroid. Using the power of the sun to push dangerous rocks out of the way may not be so far-fetched after all.
This is a typical near-Earth asteroid. Its name is Galevka. It's about half a kilometer across. It's a hazardous asteroid. Its most likely fate is going to be to strike the Earth someday, thousands of years from now.
Modern-day researchers like Eric Asfaug say the idea of a giant orbital magnifying glass to burn space rocks could work.
You create a vapor plume in one direction, and that starts the asteroid moving in the other. It's a very gradual process. It's not going to happen instantaneously. You need to know where this guy is 100 years or 50 years ahead of time. But if you do, you've got all the time in the world for a satellite to sit there, no human intervention whatsoever, and it'll gradually shove the asteroid into a different orbit, and it'll miss the Earth.
Some of the technology to do this already exists. Take an inflatable parabolic antenna the size of a tennis court, convert it to a solar collector, and use it to focus sunlight on an asteroid. The Russians have built and are testing a giant sail that captures the minute pressure of sunlight. Just attach the sail to an asteroid and let the rock hitch a ride to someplace else. But using the sun to save the Earth means waiting for nature to do the work. If we don't see an asteroid until the last minute, solar power would be too little, too late. A nuclear electric plasma engine could push an asteroid out of harm's way. The rocket technology at this NASA lab in Houston, Texas, could provide the power for a space tugboat. A group of astronauts and aerospace engineers is designing the B612 mission to prove that asteroid deflection can be done with existing technology.
These are rockets that have very tiny amounts of thrust, but they are so frugal in the use of propellant that we can keep the rocket going for periods of the order of a year.
Building a better rocket engine is only the first step. Figuring out how to latch on to an asteroid, point it in the right direction, and push without losing control is the really tricky part. After years of research, NASA finally had it, the first complete draft of a plan, a demonstration mission, to save the planet.
The asteroid off the impact with the Earth 10 years later so that it misses the Earth, and not just miss it randomly, but miss it very precisely so that we don't simply pass on the problem to our grandchildren.
Midway through 2003, the SpaceGuard survey had reached the halfway point. A little more than half of the kilometer-sized near-Earth asteroids had been located, and the news was mostly good.
For the 60% that we have already found, I can tell you that there is not a single one that poses a danger. For the 40% that we have not yet found, I can tell you nothing. One could hit tomorrow. Not very likely, but until we've found them and cataloged them, we won't know.
But finding the really big asteroids, those 1-kilometer monster rocks capable of ending human civilization, is only the first part of the challenge. There are an estimated 50,000 smaller asteroids that are big enough to cause tidal waves or destroy vast regions of the Earth.
A 200-meter asteroid happens maybe once every 10,000 years, but that's like 600 megatons to 800 megatons exploding in one place.
Recall the small 60-meter rock that exploded over Siberia in 1908? Well, even though it could have destroyed a city like London or New York, rocks that small are not included in the current SpaceGuard survey, meaning no one is officially looking for them.
Which, of course, is the same thing as saying that chances are enormous that a Tunguska-sized object will find us before we even see it coming, as happened in 1908. That is likely to happen nowadays, that we won't see it coming.
There has been talk of expanding the search to include smaller asteroids. It'll take more and bigger telescopes and, of course, more money. But until we do, we'll have no idea where those city-killer rocks are.
Evolution on Earth has proceeded in part because every so often a global catastrophe comes along, pushes the reset button, and new things happen.
It wiped out the dinosaurs 65 million years ago, and at the time, we mammals were just furry little creatures burrowing around in the ground, and an asteroid or a comet impact took out our principal competition.
I guess we are saying implicitly, if not explicitly, that we want to do away with that natural cycle.
We've had enough evolution. We like ourselves on the top of the ladder. And we can do something which will change cosmic evolution from this point forward in terms of life on Earth.
Dinosaurs ruled the Earth until a big rock wiped them out. The question is, will another rock do the same to humanity?
Let's get a couple good pictures here.
Humans are the first species with the potential to block a doomsday rock and switch off the evolutionary reset button.
People
very often say, look, you're just a doomsayer. You think that these awful things are going to happen. I'm not that way at all. I'm entirely optimistic. The way in which I view asteroids and comets and the possibility of them hitting the Earth is that it's a great challenge. Thank goodness we've realized the hazard and the danger before the next one happens. It's given us time, we hope, to do something about it.
Scientists can study the sky and find the dangerous rocks ahead of time. Astronomers can do the math and predict the orbits. People have the desire and the right stuff to do the job. There's a whole new field of science that could give humanity an option the dinosaurs never had.
Cassini space probe approaches the ringed planet, Saturn, and its 56 moons. It discovers something almost unimaginable, conditions that might support life. And if those conditions could exist so close by, what might we find in the next galaxy? On a planet just like Earth. For millennia, we humans have looked to the skies and wondered whether we're alone in the universe. Today, we're closer than ever to knowing the answer. Some scientists believe we'll get our first look at our extraterrestrial cousins in the near future.
I hope it's in the next 10 years, and I'm ready for it next week, so the sooner the better.
What's more, we could find these aliens not on distant planets in unexplored galaxies, but right next door in our own solar system. Scientists are now honing in on proof that ET is out there and living on the most hazardous of worlds. Our safari will journey to 7 destinations in our solar system to see just where these creatures could be and what they might look like. These exotic lands are unimaginably harsh. Life as we think of it would perish in an instant. But alien life may be far tougher than we expect, as we're learning from a surprising group of living things right here on Earth. Until just a few decades ago, we were sure our planet was unique. It is the only one we've found so far that has nurtured the evolution of millions of species. Thanks to its abundant sunshine, warm water, and protective atmosphere. We logically concluded that life needed each of those things, a conclusion that ruled out all other known worlds in our solar system. But then, biologists began combing some of the Earth's darkest and coldest places. And to their surprise, they found living, breathing creatures. Biologists call these organisms extremophiles. Some don't need light or oxygen. Others survive in tremendous atmospheric pressure. It seems life can turn up practically anywhere. Take Antarctica. After years of searching this arid, frozen landscape, scientists doubted they'd find anything alive. But in 1999, a team of explorers unearthed a rock from 6 feet under the ice. What they found amazed them. When they cracked the rock open, they found it teeming with tiny creatures. Here, at temperatures of 68 degrees below zero and 6 feet under solid ice, life had found a foothold.
Biologists have been increasingly discovering life, not kangaroos, but, simpler forms of life that live at very cold temperatures, very high temperatures, very great pressures, even in places where there's sort of high degree of radiation. It turns out life is able to live in a much wider variety of environments on our own planet than we used to think.
And if life can survive extreme conditions, not just here at home, but elsewhere in our solar system, think of what this could mean.
Unless there's something extraordinarily miraculous about our solar system or our planet, then life has got to be extremely commonplace. I mean, there's got to be large numbers of worlds with life, and some of them would have cooked up intelligent life.
In the beginning, our Earth was as deadly a planet as any. Over the first billion years of Earth's existence, cosmic debris pummeled it mercilessly. The impacts turned its surface into a broiling, seething inferno where life was impossible. But once the solar system settled down and the Earth began to cool, water appeared, setting the stage for life. In 1953, researcher Stanley Miller proved in a lab experiment just how easily life on Earth got its start. He combined water with hydrogen, methane, and ammonia, components of the Earth's early atmosphere. Then he zapped his solution with an electric charge to simulate lightning. His results shocked the world. Miller had created organic molecules called amino acids, the protein building blocks of all living things. If lightning helped jumpstart life on Earth, could it have done the same on other planets? Galactic probes have now found the ingredients in Miller's experiment throughout our solar system, including one essential to life.
One of the requirements that every form of life that we know about on Earth has, every single one, is liquid water. We've used evidence for liquid water to kind of guide our search for habitable environments.
Our safari is headed to 7 worlds, some possibly rich in water, where scientists believe aliens might be hiding. While any life there might have begun much like life on Earth, how it looks now is anyone's guess. We begin in the world that has always fired our imaginations, the planet right next door, Mars. Of all the planets where we've looked for life, it's the one we've studied most. The scientist who may get the first look at Martians, if they're found, is Steve Squyres, principal investigator for NASA's Mars rovers.
Mars has always had, among all the planets, I think, a special fascination for humans. For a very long time, we've known enough about Mars to know that it is probably the most Earth-like.
It may be the most like Earth, with an atmosphere and seasons, but we humans would perish quickly on Mars. Its air is thin, 40 times thinner than the air at the top of Mount Everest. And it sits in a bad neighborhood of our solar system, near an asteroid belt. Its atmosphere is too flimsy to protect it. Asteroids continually bombard its surface. Violent winds can whip Mars's sandy soil into storms that consume the entire planet for weeks and spawn tornadoes 8 kilometers high. Midday temperatures at the equator of 1 degree Celsius fall to -70 at night. David Grinspoon is a curator of astrobiology at the Denver Museum of Nature and Science. As he sees it, Mars would be warmer if it wasn't a planetary runt.
When I grab coffee on a cold morning, I know that a small espresso is going to cool off quickly, whereas a larger coffee is going to stay warm much longer. Large objects stay warm longer because their interiors are shielded from the outside where the cooling occurs. And planets are exactly the same way. A small planet will cool off early in its history. A larger planet like Earth will stay warm for billions of years, which makes it a better place probably to look for life.
Despite Mars's drawbacks, it has always fascinated scientists because its terrain seemed to give evidence that it might support life. Its dynamic landscape of mountains, volcanoes, and deep ravines is not unlike our Earth. To early astronomers, these features look like oceans and rivers, and even a system of canals, supposedly not just supporting life, but actually produced by it.
Percival Lowell in the United States observed these things and inferred that, in fact, these things were so straight and so regular in geometry that they had to have been the product of intelligent life. Okay? Well, he was right. The problem was the life was at the wrong end of the telescope. In viewing this thing visually through a telescope eyepiece, the human eye-brain combination started to connect things that weren't really there.
Lowell was not alone. Some scientists were shocked when the probe Viking 1 beamed back this image. Is that a human face? Perhaps produced by Martians in their own likeness? Until recently, we've never really known where to look in our solar system for extraterrestrial life. But we've always known what the aliens would be like once we found them.
Consciousness. I was on a table.
Usually, there is more than a hint of the Earthling in our aliens. Hostile or lovable, they tend to resemble mutant images of ourselves. As a senior astronomer at the Search for Extraterrestrial Intelligence Institute in California, Seth Shostak has spent his career listening for the radio waves of a distant alien society.
There's no reason to assume that they're going to look like us or even think like us or behave like us or have language. You know, you just have to look at the variety of life on Earth and you see that, you know, nature can come up with lots of different forms.
But if there is life on Mars, how could it survive in such extreme conditions? Since the 1960s, scientists have sent dozens of probes to the Red Planet. The first pictures of the barren landscape quickly dashed any hope of finding intelligent beings. But what scientists did see startled them. Though there's no evidence of Martian-made canals, there are signs that Mars actually may have had water. Some think the angry red planet might once have been blue.
You just have to look back a couple of billion years, 3.5 billion, 4 billion years ago. Mars had a thicker atmosphere, had water on its surface clearly, maybe it developed life. And as it slowly went bad, you know, the life had to adapt.
Life may have adapted, not died off, because some liquid water may still exist underground. But with no surface water, frigid temperatures, and ultra-thin atmosphere, Mars is a planet only one kind of creature could love. An extremophile. Extremophiles thrive in the cruelest of places. To see where they might lurk on Mars, we head to the Valles Marineris, a massive rift in Mars's surface, 20 times wider than the Grand Canyon in places, and almost as deep as Mount Everest is tall. Lakes may have once flooded this valley, and those lakes could have hosted life. As the water dried up, life could have evolved to cope with the harsher environment. We won't know what these extremophiles are like until we find them. But they may resemble creatures that exist in extreme places right here on Earth. An unusual team of biologists, called astrobiologists, study Earth for the kinds of life we may find in outer space. Astrobiologist Rocco Mancinelli is on the hunt for Mars's extremophiles.
If it went beneath the surface, and some of it undoubtedly did, then what happened to it? Well, it formed brine pockets. So what kind of organism can live in a salty brine? A salt-loving organism.
Astrobiologist Chris McKay thinks he knows the kind of salt-loving creatures that might survive on Mars. Creatures much like those he's found in one of the driest, saltiest places on Earth.
The fundamental challenge to life on Mars is, in a sense, the fundamental challenge of life here in Death Valley. It's dryness. That is the hardest thing for life to adapt to.
Thousands of years ago, a salty lake covered Death Valley, just as lakes filled Mars's Mariner Trench.
Move in closer. This is still wet, a little wet. This appears like a lifeless place, a big, flat, white, empty horizon. But yet, just below the surface, we find layers of algae and bacteria growing. They're living in an environment that in many ways is fundamentally different from the environment that we sense on the surface. Here you're in a place which looks lifeless, looks dead, and yet you dig down and hidden underneath, there it is.
Beneath the salt is a layer of hardy green algae that survive on the water and light that trickle through. The algae in turn feeds salt-loving microorganisms.
Here in deserts on Earth, dried, salty lake beds, we're going to find them on Mars as well.
Salty deserts are not the only places life might be hiding on the red planet. There are Mars's tremendous volcanoes, some of them 6 times larger than those on Earth. Astrobiologist Penny Boston studies the caves, called lava tubes, left over after volcanic lava has dissipated. Not long ago, we assumed caves like these were devoid of life. They get no sunlight, and no sunlight means no photosynthesis. But in lava tubes outside Albuquerque, New Mexico, Boston has found evidence of extreme life.
Because we know Mars has many, many lava tubes. And so here we have the opportunity to see how these formed and also to look at the life that inhabits them.
The extremophiles Boston has found appear to be thriving. They get their energy by feeding on the minerals in the cave wall.
So here we're up close to the wall, and you can see these white patches here growing against the black basalt. And each one of these is like a major city for these little guys. And they're all nestled in these little pockets in the basalt. And so these guys are permanently adapted to these freezing temperatures. They never see any light, and they get what they can find in the environment.
Are there creatures like these in the caves below Mars's volcano fields? Boston thinks so.
We are going to find life, and I just hope that I live a long and healthy life so that I can still be around to see that.
We may already have had our first glimpse of Martians, not from our visit to their planet, but from their visit to ours. 16 million years ago, an asteroid slammed into Mars and propelled a 2-kilogram rock into space. Amazingly, that rock sailed to Earth and came to rest in Antarctica. Inside, NASA scientist David McKay and Everett Gibson were amazed to spot the outlines of fossils. Water has carved small tunnels in the rock. And in these tunnels, McKay and Gibson found what they believed to be evidence of bacterial life.
These are little microbes, and they're dead, and they're fossils, or in some cases, we don't even see the forms. We see the footprints or the evidence that they were there.
Life from Mars? Maybe. The hunt is only just beginning. NASA plans to send a rover called Phoenix to Mars. it will study the planet's ice cap and probe 3 feet beneath the surface. NASA even has a plan to send human visitors. They may not meet the little green men of our imaginations, but they could encounter life in some form. What will it look like? It is likely to be a subterranean dweller with an ability to survive on little water. Perhaps an organism with a taste for minerals, like the creatures in the lava tubes of New Mexico. Even the smallest find would have enormous implications. Proof that life is not unique to Earth, but exists just next door. Our safari to the places in our solar system likely to harbour alien life now takes us past the asteroid belt on the far side of Mars. Here, Jupiter reigns. But this planet, the largest in our solar system, is fairly hostile to life, thanks to its toxic gases and overpowering gravity.
Not only is it pretty cold out at Jupiter, it's also, it's got this really thick atmosphere, tens of thousands of miles thick, and it's got ammonia and methane and, things used to clean the bathroom. But Jupiter has more than 60 moons that we know about.
At first glance, those moons would seem unlikely places to seek alien life. Their atmospheres are thin, and they are inhumanly cold. The temperature on Callisto is lower than -200 degrees Celsius. The scientific probes Voyager and Galileo have detected little on the surface of these moons but ice, with one dramatic exception. Io is one of the closest moons to Jupiter. When NASA sent Voyager 1 to Io in 1979, astronomers were astonished to find its surface roiling with giant volcanoes.
Io is the most volcanically active place in the solar system, just spewing volcanic material from its surface all the time.
What could be heating the interior of this frigid moon? Amazingly, it's the force of gravity from Jupiter. The giant planet exerts enormous gravitational pull on its moons. The closer the moon, the stronger the force. So strong, it can actually stretch their crusts. But some of these moons have elliptical orbits, so as they near Jupiter, the crust stretches towards it. When they move further away, the crust relaxes back towards spherical. This constant tidal movement creates friction deep inside, and that friction generates heat. It's like rubbing 2 sticks together to start a fire. The pull of Jupiter is heating Io from the inside out. Volcanic fumes and lack of water make Io inhospitable to life. But Jupiter's other large moons are more distant, close enough for Jupiter's gravity to warm them from within, but distant enough to remain calm on the surface. 3 of them look particularly promising as possible homes for alien life. The one furthest from the giant planet, Callisto. On its surface, Callisto looks like our moon, scarred and cratered by countless hits from asteroids. Those impacts may have melted the surface ice for brief periods, allowing life to take hold. But in 1998, the Galileo spacecraft detected a much more promising incubator deep beneath Callisto's surface. Radioactive rocks and tremendous pressure in its core generate heat inside Callisto. The heat may be melting its icy crust from below, creating a hidden ocean. And hidden oceans could mean hidden life. As we fly closer to Jupiter, we find its largest moon, Ganymede. Ganymede is also deeply scarred. Ridges rise above its surface. Those bright spots are craters as big as 5 kilometers across and likely to be lined with frost. But these photos offer the most compelling clues to where life here might hide. They show flowing glaciers, glaciers that resemble those on Earth. Ganymede's moving glaciers could also be signs of heat within. So, like Callisto, Ganymede could also have a hidden ocean, buried beneath as much as 190 kilometers of ice. The third moon on this leg of our alien safari is the most intriguing. It is called Europa, and of the three, it resides closest to Jupiter. That proximity to the giant planet means Europa's core may be very hot, far hotter than Callisto's or Ganymede's. But its surface remains frigid, a potent combination for life, since there could be a temperate zone where they meet. Mammoth fissures scar Europa's thick crust of ice, a sign that ice is always shifting. On our own planet, we see the same cracks in the ice sheets covering the Arctic Ocean. Europa's crust may be riding the largest ocean in the solar system, an ocean twice as large as all of Earth's put together.
Now those oceans, if they're there, and the chances are pretty good that at least some of them are, they've been sitting around for a long time, 4 billion years, a little longer, right? In 4 billion years, an ocean of water, do you think anything might have cooked up there? Well, it certainly seems plausible.
The environment in Europa's ocean is more or less as nice as the environment in our own ocean, as a place for living things to exist. Heck, things from planet Earth could probably live in the European Ocean.
But Europa's oceans will be very cold, even slushy. And sunlight never penetrates them, thanks to an icy cover that may be 16 kilometers thick. We might never have thought life could exist here, if not for a revolutionary discovery off the coast of Ecuador. Deep in the Pacific, biologists have found flourishing communities of tube worms, crabs, and even squid. These creatures are thriving despite complete darkness, extreme cold, and the pressure of the deep ocean. They feed on bacteria that take their energy not from the sun, but from chemicals erupting from the sea floor. We might find very similar volcanic vents on Europa, supporting their own web of life. To find out, NASA scientists would like to put a lander on the European surface. Some would like to send a cryobot, a robot that would melt the ice and release a probe into the liquid below.
That's not so hard to do. You just have to melt your way through. But you're going to have to melt your way through not a couple hundred feet, but maybe a dozen miles of ice. And send down a fishing line with maybe a video camera and a light bulb on it and look around.
In all that water, we can't rule out the possibility that very simple life forms have evolved further. We might even find creatures as advanced as some here at home. Most likely, however, we would find microbes. But even that would be a sea change in how we view the birth and growth of life. Europa was warm. What if the place is one of the coldest known? Or if its lakes flow with toxic chemicals instead of water? These are the worlds we find as our safari continues even deeper into space. As our safari in search of alien life sweeps by the ringed planet, Saturn, we can see the violently swirling gases that choke its atmosphere. We can also feel Saturn's gravity, weaker than Jupiter's, but still formidable. We'll keep moving. We're not likely to find living things here. Saturn's rings are also extremely inhospitable. They're made of rock and ice, as small as a grain of sugar or as big as a house. But Saturn has many moons, 56 that we've spotted so far. Our safari heads first to one of those moons, a tiny frigid satellite called Enceladus, just 500 kilometers in diameter. Here, gravity is very weak, a fraction of that on Earth. And Enceladus has hardly any atmosphere. It reflects back into space almost all the sunlight that hits it, making it the shiniest object in our solar system. Until very recently, we also thought Enceladus was too cold to support life. It appears we were wrong. In 2005, after a 7-year journey, the Cassini spacecraft approached the tiny moon and detected something that stunned the mission's principal investigator, Caroline Porco.
So this was the picture that just, you know, grabbed us. Just was shocking.
Those are plumes made of water from a geyser. The geyser's steam and hot water hit the cold vacuum of space and explode into a jet of ice. With little gravity to rein it in, the ice cloud can grow as big as Enceladus itself. Porco has never seen anything like it anywhere else.
It's like a planetary explorer's dream to come upon a body like Enceladus. Those jets, those fountains, if you will, just spewing vapor and icy snow hundreds of kilometers above the south pole of Enceladus.
There's only one conclusion. Tiny, frigid Enceladus is piping hot within. Like Jupiter, Saturn's giant gravitational field tugs on its satellites, creating friction and heat within.
As far as we can tell now, it seems like an inescapable conclusion that there may be liquid water deeper down on Enceladus because it's warm. And the best models we can put forth right now to even explain the warmth, much less the jets, seem to indicate that you would get temperatures warm enough to melt water.
Heat, liquid water, even the furthest reaches of our solar system may contain the chemistry for life. What kind of creature could live in the steamy waters of a geyser? Thanks to hot springs back on Earth, we have some idea. At one point, we assumed nothing lived in the steam-driven fountains of Yellowstone National Park. But then, biologists discovered microbes in these waters. Microbes that feed on chemicals dissolved in the water. Today, we call them thermophiles. The hardiest can thrive in boiling water. Could there be thermophiles on Enceladus? To find out, our safari takes us in for a close-up of this extraterrestrial Old Faithful. It's too cold for anything to live near the surface, but temperatures there are minus 165 degrees Celsius. But what about the hot water inside? In the ice plume above Enceladus, Cassini's probes have found carbon dioxide and methane, chemicals that could feed life below. Just as the chemical-laden springs of Yellowstone feed microbes living there.
We have a body that very, very likely has liquid water in its interior, has shown us already it's got simple organic compounds, and you know, a whole host of things that make it, I think, a major body of astrobiological interest in our solar system.
If Enceladus has been a shock, astronomers have been astounded by another of Saturn's moons, Titan. It may be the unlikeliest to harbor life. Titan gets only a limited amount of sunlight, about 1,000th as much as Earth. Probes sent to Titan have detected ice, but no liquid water. And at temperatures of minus 138 degrees Celsius, that ice is hard as stone. What could possibly make Titan a promising environment for alien life? Remarkably, Titan in many ways resembles the Earth, but not the one we know now.
Titan has turned out to be the body fantastic in the Saturn system, which is long suspected of having an environment at the surface, not only similar to the kind of environment we find here on Earth, even, believe it or not, similar to the kind of environment we had on Earth before the emergence of life.
Titan intrigued Carolyn and Porco's team so much, they directed the Cassini spacecraft to send a probe there in 2005. It was the most distant surface mission ever conducted. The probe saw just ridges and plains. But a later flyover by Cassini spotted a shoreline. Soon, thousands of lakes came into view, at least one bigger than the Great Lakes of North America. It's the first time we've ever detected liquid on the surface of another celestial body.
Kind of looks like Minnesota, except the lakes are not water, they're liquid natural gas. But liquid natural gas is a liquid.
And that's not snow. Those are methane flakes. Like Earth, Titan has weather, but it's of a rather psychedelic kind. There are even methane hurricanes.
It's not water, it's methane, doing all the exact same things. Raining, evaporating, flowing in rivers. So you have something that is basically doing what water does on Earth. On Titan, only it's methane.
A similar scene may have existed on Earth 4 billion years ago, making scientists suspect that Titan could also be an incubator for life.
Chemistry does go on. At those cold temperatures, it's really slow. But Titan has had 4 billion years in which to do some chemistry, and maybe in that period of time, maybe something is cooked up.
It would have to cook up without liquid water, something we've never seen before. But scientists aren't ruling it out. The substitute could be the methane, so abundant on Titan. Used for fuel on Earth, methane was long thought poisonous to all life. But in 1997, researchers examined mounds of methane ice in the Gulf of Mexico, and they were astonished to find colonies of small centipede-like worms thriving amid the frozen substance. They think the worms may eat bacteria that feed on the methane.
In general, things that we think of as deadly, many of them are potentially lively. If you can figure out an evolutionary way to tap into that energy rather than having it destroy you, then it can be bountiful.
There could be one more complication for life on the surface of Titan. With only a weak magnetic field to shield it, living things on the surface could be exposed to cosmic radiation. But that might not be a problem for an extremophile, as we found here on Earth. Biologists have uncovered plenty of life near Chernobyl's contaminated nuclear reactor. And even swimming in toxic radioactive spills, actually feeding off the decaying molecules. It's possible Titan's life forms could do the same. To find life on Titan, we may have to dive into its methane lakes, where we might find chemical-loving bacteria. We may even find microbes resistant to radiation, not unlike those here on Earth at Chernobyl, living on its rock-hard ice sheets. Organisms that eat methane might give off heat, melting the ice, possibly creating another fountain for life. There's no doubt, life on Titan would be a strange brew. But we have yet to visit the most bizarre world where scientists believe life could exist. And it's much closer to home. Our safari of the world's most likely to harbor alien life has taken us far. We've visited frigid deserts, submerged oceans, and methane lakes. But the world we are about to visit may be the most extreme of all. For our final stop, we are turning back toward Earth, to Venus, our closest planetary neighbor in the solar system. If life can survive here, it seems it could exist almost everywhere. To reach the surface of Venus, we have to fly through a dense layer of yellow clouds, 64 kilometers deep, with a composition similar to battery acid. The atmosphere here is 90 times heavier than Earth's, too heavy for a human to tolerate. On the ground, there are extinct volcanoes and lava flows as far as the eye can see. They cover 85% of the planet's surface. It is hard to believe Venus once had vast oceans.
You basically had a runaway greenhouse effect, where as it starts to get warmer, the oceans start to evaporate, and then that puts water vapor in the air. Well, water vapor is a potent greenhouse gas, so that's what leads to the runaway. The oceans basically boil off, and then the CO2 all ends up in the atmosphere, and so today you have this very hot, hyper greenhouse planet.
With temperatures around 460 degrees Celsius, Venus is even hotter than Mercury, the planet closest to the Sun. Not a surface hospitable to life.
Life, as we know it, cannot exist on the surface of Venus because organic molecules would just be ripped to shreds by the hot gases.
But we've stopped here, not because of what's on the ground, but what's in the air. In 1982, the Soviet spacecraft Venera 14 visited Venus. In the clouds, 50 kilometers up, it detected temperatures much cooler than on the surface. What's more, it found the molecules so critical for life, H2O. So far, every bit of water we've found beyond Earth is frozen solid. Only in the clouds above Venus have we found it in vapor form, a possible incubator for life. But Venus's clouds are also filled with highly acidic sulfur. Once, we thought nothing could live in sulfur. But scientists have analyzed some of the most acidic water on Earth, leaching from a California mine.
Watch your head, Dick. Sulfuric acid.
In sulfuric acid strong enough to erode metal, eat through clothing, and dissolve human flesh, they found life. Acid-loving extremophiles. These organisms feed on sulfur compounds, like iron sulfide, eating the iron and emitting the highly acidic sulfur. Do extremophiles like these float above Venus? Astrobiologist David Grinspoon likes to think it's possible.
Maybe in the clouds of Venus there are some sulfur-based organisms. Sulfur actually absorbs ultraviolet light in interesting ways, and I'm just imagining that there's maybe some kind of photochemical reaction going on where ultraviolet light is actually being used to convert chemicals into some higher energy state, which then is basically being eaten.
What will these aliens be like if we do find them? They would have to tolerate high temperatures and enormous atmospheric pressure. They would also need to thrive in acid concentrations deadly to most life forms. Perhaps they might resemble a hardier version of the acid-resistant extremophiles in California's mine.
We keep finding that life lives in places that we used to think were inhospitable. So whenever we say, oh, it's impossible, you couldn't have life in the clouds of Venus, I think we have to be very careful because they might just reflect our own ignorance or our limitations on our own imagination, and maybe not real limitations on the ultimate creativity of nature, which seems to find solutions to these problems.
As our safari returns to the cool, blue, lush and lively world of Earth, we can see why we so revere its life-sustaining gifts. But, as we are learning, even the most extreme environments can harbor living things. Extremophiles may resemble the first version of life in our universe, and they could even be the most common. Could they have evolved further from these humble beginnings? Could intelligent life be out there as well? For more than 40 years, scientists at the Search for Extraterrestrial Intelligence Institute in California have been searching the skies for answers to that question. Astronomer Seth Shostak believes he'll know the sound of alien life when he hears it.
We have a couple of observing projects to try and find signals. The biggest one are our radio searches, and that's where we use big arrays of antennas, and we point these antennas at nearby star systems that we think, well, this is the kind of star that might have a planet that might be something like Earth. We point in those directions, hoping to pick up a signal that would tell us that somebody there is clever enough to build a radio transmitter.
It's a safari that never leaves home. Astronomers have also recently captured enough light from planets in distant solar systems to deduce their chemical makeup. They have found elements that may help form RNA, one of the building blocks of life here on Earth. And 20 light-years away, in the constellation Libra, a team of European astronomers has found a planet that could be warm enough to have liquid water on its surface, just like Earth. Meanwhile, headed to the furthest reaches of our galaxy are 4 spacecraft launched in the 1970s. Aboard 2 of them is a map of our solar system and the image of a man and a woman. 2 others carry a sample of uranium, whose rate of decay would date the probe, regardless of language. The 2 are also carrying what could be the most universal message of all, a recording that includes a composition by Bach. Just don't expect news anytime soon. These intergalactic postcards from the Earth will take 80,000 years to reach the nearest star. Our search for life beyond Earth has only just begun. There are billions of planets yet to be explored. Every one of them holds the tantalizing possibility of life. Even intelligent life.
Just in the face of this enormity, the idea that we're the only game in town, it just doesn't seem reasonable.
I think the question of whether we're alone is profoundly important for human beings in general. If you're aware, you really have to ask that question.
Somewhere in a galaxy, known or unknown, something or someone could be looking out into space, peering at the Milky Way and wondering, is there life out there?